Hey, good morning, everyone. I'm Grace Simmons, Head of Learning and Engagement at NLA. Welcome to this morning's technical briefing, TM65 Embodied Carbon in Building Services in association with Introba. For those of you not familiar with NLA, we are London's built environment community. For access to hundreds of events, research, exhibitions, and critical industry insights, you can become a member for as little as £20 per month. So this event is part of the NLA technical program, and we're very happy to have Introba with us today. I'm sure you'll have some questions for our speakers, so please feel free to send these through during the presentation using the Q&A button on Zoom, and we'll come to them at the end. So I'll now hand over to Yara Maknouk, who's the associate at Introba, and Miguel Lopez, senior embodied carbon engineer at Introba.
Sorry, just getting control of the screen. Perfect. Okay, thanks so much, Grace. Good morning, everyone, and thank you for joining. As Grace mentioned, we'll be talking about TM65 today, which is a methodology on calculating the embodied carbon of building services. Just to quickly, I guess, introduce ourselves. So we're from Introba Consulting, building services and sustainability engineering company. In the UK, but also an international firm. And we're really excited and pleased to have been involved in authoring CIPSE TM65, as well as the papers that came after it, which we'll be talking through today. I'm Yara Mishnook, an associate with Introba. And Miguel, do you want to quickly introduce yourself as well?
Sure. Hi, everyone. I'm Miguel Lopez. I'm a senior embodied carbon engineer in Introba. I come from an architecture background, but kind of like tread the line between architecture and engineering, and I'm just happy to be here. Yara.
Great, thank you, Miguel. So, just to quickly, I guess, cover what we'll go through today. We'll kind of start a little bit at the beginning of just a general introduction to what embodied carbon actually means, what are the factors that affect it, go into what this means from a whole building basis, so not just MEP, which will be the focus of our session, but kind of how other factors of the building layers affect the embodied carbon and the whole life carbon of the building. Cover a few general design principles that I think as designers, industry professionals, we should be aware of when being involved in building design, and then the impact of MEP. How substantial is it, and how does TM65 help to solve this problem? We have been, I guess, at Introba over the past 4 years since it's come out. We've been talking about TM65 a lot, whether it's with other industry professionals, whether it's with manufacturers, and we feel like it's, kind of widespread and it's being used across the industry. It's been mentioned in kind of new methodologies. It's mentioned in regs. It's mentioned in LETI guidance and so on. But we do understand that kind of at a first glance, TM65 can seem a bit overwhelming. So we're really hoping to break it down today, simplify it, and also give you kind of the best places to get resources from the different TM65 documents. And before we get into that, as I mentioned, we'll start with general introduction and just some definition setting before we kick off. So I'll hand over to you, Miguel.
Sure, thanks. So next slide, please. We wanted to start, first of all, acknowledging why we are even talking about this. And this figure for 124 parts per million, that's the amount of CO2 in the atmosphere around March of this year. That doesn't really mean much without any context. Next slide. But when we put it in the context of the past 800,000 years, which we can see far from data on fossil records, we can see that we are way above the natural cycles on the Earth. It is true that this is kind of like one of these myths, like, oh, climate is always changing. And we can actually see, yes, there's in fact some ice ages when the concentration of carbon is in the lowest, and then some interglacial periods when it's at its highest. But we have basically broken the system with the current emissions. Next slide. And just for context, what this means, from the highest point to now, it's basically the same amount of difference in carbon as from that to a glacial age. Normally, the amount of carbon that the Earth would add to the atmosphere in 20,000 years, we have added in 200. So we're talking at changes at a planetary scale at this level. So this is very important, essentially. And when we start to point fingers or see like, okay, who's responsible? Actually, the building sector is responsible for around 39% of all emissions between running the buildings and actually building the buildings. And that's what we call the two different types of carbon emissions, which are operational carbon and embodied carbon. Operational carbon, again, is the carbon emissions associated with energy and water during the building lifetime. So essentially, again, running, using the building. And embodied carbon is the amount of CO2 and other greenhouse gases emitted during manufacture, transport, and construction, together with the end-of-life emissions. Next slide. So when we look at whole life carbon, we try to look at the entire life cycle of the lifetime of the building. We can see in the lifespan in that chart on the left, how there's some initial emissions being emitted. That's the embodied carbon from up to the construction stage. Then during the use of the building, there's some emissions happening every year and year. And then there's some emissions at the end during the end of life. When we speak of, can we move you back? When we speak of embodied carbon, if you look to the right, we basically are speaking of stages A, that's the construction stage, B, that's the use stage, except energy and water, and C, that is the end of life stage. That together makes embodied carbon, which is going to be the bulk of this presentation. And then there's stage D, which is beyond the scope, which is the potential for recycling and reusing. So what happens when only one of them is addressed? So a typical building had normally, years ago, a massive operational carbon and a smaller embodied carbon. But through decades of investment and investment in renewables and improving thermal performance on all these measures, essentially the operational carbon part has been shrinking while the embodied carbon part has been remaining essentially the same, which means that we believe that we're doing a great job, which we are in the operational side, but we're ignoring the other half of the equation entirely. So some high performance building could be great for operational, but still have a huge embodied carbon sticking out. And the actual carbon footprint is much bigger than what you expect. So how do we solve this then? We have to acknowledge both sides of the equation, not only the energy side and the operational, but also it's essential that we acknowledge the emissions and the impact the materials have. So how do we actually go around with measuring this? We do this with an LCA, also known as life cycle assessment. And essentially, it's a standardized methodology to associate the environmental impacts of a product in all of its stages. In this case, the product is a building, but we can do an LCA of anything, basically. And when you do an LCA, you can get environmental impacts that go way beyond carbon and throughout other things, for example, ozone layer depletion. But for today, we're just going to focus on greenhouse gases. The unit that is always used, the standardized one, is kilograms of CO2e. The E stands for equivalent because basically we acknowledge that there's more than one greenhouse gas involved, like methane, but it would be just a chaotic mess if we tried to acknowledge every single gas separately. So we just put them all together in what would be equivalent greenhouse gas, so greenhouse effect of carbon dioxide. So we just put everything carbon dioxide, but we acknowledge there's more than one greenhouse gas involved. So the way that we do this is with an EPD. And essentially EPD stands for Environmental Product Declaration. And it's kind of like an LCA, but for a product, essentially. It's a standardized way to get all the information as to what are the environmental impacts of a product. It can be a brick. It can be spray polyurethane, like in the example. I always compare it to kind of like the nutritional label in food. It gives us in transparency and detail what are the nutritional value, the environmental impacts of all of this product in a way that's clear and comparable between them. So essentially, the equation is actually quite simple. We need to understand how much in this case, for example, 5 kilograms of a material. We can get this information from volume, weight, area, whatever unit we can use to quantify it. This can be obtained from BIM, from Revit, from anything. Then you multiply that by the EPD information, the carbon factor. So for example, the material has 2 kilograms of CO2 per kilogram of material. Well, the total is 10. So essentially, this is a very simplified way. There's much more variables going on here, but this is the bulk of it. We always look at either the material quantity, trying to optimize that, or the material itself, the carbon emissions associated with it. So some very, very high level general design principles. Regarding the structure is normally the most impactful component of a building. This is just because of the materials used and the weight that it has. To begin with, I think the most important thing is to consider the different material options. There are opportunities and consequences for each. Mainly, I'm speaking timbers, concrete, or steel. Concrete is the most carbon intensive. It is one of the most or the most carbon intensive materials out there due to many different factors. But essentially, timber is currently the key to low carbon buildings. And any low carbon building currently uses timber to a certain degree or is reusing structure. Then for the weight, the leaner the better. Again, we're trying to play here with the quantities. If you can do a building with less materials, then down the line, that's always better. You can either use this with reusing, again, key, or trying to have very lean, efficient structures. If, for example, you use timber as well, you can have lighter structure, which means smaller foundations, again, less materials. Complexity. If you have an overly complicated building with an overly complicated structure, that could also be a hindrance in the amount of materials that we're using. And the grid size as well, large grid spans will mean deeper beams, thicker slabs, again, more materials, worse down the line. And for facades and interiors, this is where we can get a bit more nuance. For example, different material options. In this case, we can use natural materials for insulation like cork or hempcrete, straw bale even. These are great insulators and they're natural in origin, which means that they haven't really used any carbon and they actually store carbon in them. Performance components, it is very important when we're talking about facades that we consider the lifetime of the service life of the materials. Sometimes it's best to spend a bit more money into a high quality window that will last you 20, 30 years compared to like a cheaper one that would last you 10 years and then you have to replace it again and again and again. That's carbon down the line as well. And as well as structures, simplify, standardize. The more simple things, the more lean and less materials you use. And regarding interiors, anything that you can reuse, anything that you can recycle, and reducing quantities wherever you can is always key to have a low carbon building.
Thank you, Miguel. So we'll transition on to the impact of MEP in all of this. So as you'll just have noticed, Miguel touched on some general design principles for facade, interiors, structure, and I will focus on how you can impact the MEP. So I think typically what we've seen is that kind of in the world of EPDs and general benchmarks we've seen around LCAs, historically, I'd say up until maybe around 2 years ago, it was really hard to find data on MEP systems and equipment. It's rare to find EPDs that cover a lot of MEP products, as well as understanding the range of how much MEP actually has an impact on embodied carbon was difficult to quantify. Going back to the equation of how you even how you do an LCA, it's two factors. So the quantity side was something that was quite challenging for MEP. So without we've had advancements in BIM recently, and kind of the way that we model buildings during design stages, we've been able to kind of extract quantities in a more efficient way and a more accurate way recently, which has helped fill that gap. And then in filling the gap of what is the embodied carbon for those specific products. So as I mentioned, there's always been limited EPDs for MEP products. So this is where kind of TM65 can come in and help to fill that gap here. Before going into that, just to cover why the embodied carbon of MEP even matters. So just, I guess initially what was being done was kind of a standard X amount figure for MEP was being added to every LCA. And partially because there is difficulty in understanding how to calculate it, but also I guess there is an assumption that we're not sure how big or small this number should be. So let's just go with the standard figure. But actually, when you look into it, there are some key factors which actually make the embodied carbon of MEP quite high in the overall building LCA. So there's 5 factors here that we'll quickly go through. Each of these factors will affect one of the 2 parts of the equation. So either it affects the quantities or it affects the actual GWP embodied carbon value of that material. So first of all, quantities. So we touched on the difficulty of actually quantifying what's in the building, but actually not just the difficulty in quantifying it, but there's a lot of products that go in there. So one thing with MEP is that it's typically something that we don't see in all the buildings. So it's hidden kind of underneath floorboards or ceiling tiles. So if you kind of extract that, whether it's BIM form or through building surveys or so on, with all the cables and the wiring and the light fixtures and everything going into a building, it actually amounts to a really high amount of material going into the building. As well as that, you multiply that by kilograms of CO2 that are actually quite high for the materials. So MEP product, as we all know, it kind of contains a lot of metals, a lot of rare earth materials for things like lighting and electronic components. All of those typically have really high embodied carbon values and coefficients. So combining the high quantities with the high impact materials starts to give you some really high values. As well as the type of materials, the supply chain also affects the embodied carbon. So they're key stages within the embodied carbon life cycle and transport. And kind of the way that it's extracted, the way that it's disposed, which has a huge impact. So a lot of materials, a lot of products that we see, there's a lot that comes from China, and not only do we kind of transport it from there and bring it, all across the world to be used, but it's also then transported back to be kind of disposed of, and whether it's reused or recycled at its end of life. So that also has a high impact. And one key thing to consider with MEP is that it has high replacement rates throughout a building lifetime. So if we consider the standard building lifetime span for an LCA is about 60 years, or is 60 years. If we think of the services within that, it kind of ranges between 5 to 10, 20 years, so depending on the product. So if you think of that throughout the lifetime of the product, the project, you could be replacing specific components 5 or 6 times throughout the whole lifetime. And that means you're taking it out, you're disposing of it, you're putting a new material in. So if we just compare with the 2 graphs on the right, you'll see that the top graph shows you upfront embodied carbon of a breakdown across different components. Services being what's in kind of this light blue figure here. So the upfront embodied carbon is obviously at the start of the project, and you can see MEP only contributed about 6% of that overall. There's a lot more that goes into substructure and superstructure, and the concrete and the steel and those larger components. But then when you start to look at the lifetime of the project, which is the second graph below, which looks at the B and C stages, you'll see that services jumps up to around 40%, whereas substructure, superstructure stays much lower. There's less replacements in that, but services, you're going to need to replace a lot of that every time it reaches end of life or things get worn, or so on. So something to consider with that the lifetime. And finally, refrigerants. Refrigerants is obviously a key component of a lot of building services equipment, like heat pumps or VRF systems that we're seeing more and more of. It's really important to be conscious of the refrigerant types that are being used in those products. So this kind of diagram just shows you can kind of see aluminium on the left, which is typically something that we would kind of put the biggest bubble for because it's really high embodied carbon from a metals perspective. Looking at that in comparison to some refrigerants, which we see commonly used, you can see that actually they have a much higher embodied carbon coefficient, and not just them being used in products, but also they leak over the lifetime, so that has an impact as well. And this is just a graph to show a range of refrigerants that are in the market. Obviously, different ones work differently with different types of systems, so it's not as easy as just swapping one out for the other. They also have efficiency impacts as well, but just something to consider, kind of the range of what's in the market and kind of things that should be looked at when being specified on projects. And a few design principles to cover on MEP. So we touched on refrigerant, the importance of the type of refrigerant being used, also looking at the leakage rates and the recovery rates at the end of life. Passive design is really important. So although that involves designing the building fabric and how the building is constructed, but that can have a huge impact on the size of MEP products that we're designing into buildings. And essentially with everything embodied carbon, kind of the first thing to do is design less. So that really helps with that initial first step of designing less to begin with. Optimization, so this is really close collaboration between MEP engineers and also architects to understand kind of distribution lengths, how they interact with architectural elements within the building, and that's really important. And then as well as that specification. So yeah, just specifying the right equipment has low embodied carbon values, but also equipment that's long lasting and doesn't need to be replaced as often, and that you can easily access and maintain. So how does TM65 help to resolve kind of that gap? So what TM65 is essentially it's a calculation methodology that came out, was published in around 2021, end of 2021, which helped to fill that gap of like, what do we do if we don't have an EPD, but we still want to know what the embodied carbon is of these building services and these systems that we're putting in the building? That was obviously a subsea collaboration document. And following that, there's a few research papers that have been done on different sectors within the industry, so residential heating, also looked at logistics centers, and a paper on offices is also coming out soon. So what those topic papers do is essentially pull on the methodology that was created, but apply it to systems that we're more typically seeing in each of these different typologies. As well as that, TM65 started to gain traction in different parts of the world as being a methodology that can be used in other regions. So what was done is we created kind of a local addendum, which basically means this is how you use the TM65 methodology in different parts of the world. So there was documents created for North America and Australia and New Zealand, and I believe the Middle East one as well. So it's great to see that it's also can be used in context that's not just the UK market, which is what it was originally written for. The methodology itself, so going back to kind of the life cycle stages that Miguel touched on at the start, it covers all the life cycle stages apart from obviously B6 and B7, which is the operational energy and water use. And also B4 and B5 is not included in the methodology because it refers to replacement and refurbishment that happens more on a building level rather than at a kind of product level. But otherwise, all other stages are accounted for in one way or another in the methodology. And the methodology has kind of three steps to follow. So initially, data collection. It does need collaboration with the manufacturer to get initial data to calculate what the TM65 value is for that product. There's two kind of options to go down, and we'll cover the difference between them. But there's a basic calculation route for kind of quick results, maybe early stage, and there's also mid-level calculation, which goes into more detail, but essentially needs a bit more information from the manufacturer to do so. And then there's also some standard reporting forms which come with the Subsea TM65 publication when you download it. And the reason for that is just to ensure consistency and transparency across the industry when the methodology is being used. Here we can see the difference between the basic, the mid-level, and then also an EPD. So something to, I guess, specify is that the TM65 methodology is not a permanent replacement for EPDs. It's something to kind of accelerate the progress that we can have in the industry in terms of calculating embodied carbon of building services. While EPDs become more mainstream, we start to see them for a lot more products and so on. So it's not a direct replacement, but you can see in some ways, if you look at the basic calculation, it's much less detailed. So it's something to consider that there's kind of buffer factors and scale factors applied to it. Obviously, the mid-level calculation, you start to get a bit more detail, you start to get more manufacturer involvement, and then the EPD obviously is the most detailed you can have, just because it's third-party verified. It's a very kind of standardized methodology that's been around. So that's how the three compare to each other. And here, we just wanted to show you a snapshot of results and how the basic calculation and the mid-level calculation can differ. So if you just look at the top graph, you'll notice obviously there's fewer kind of colors and stages being accounted for. There's also quite a large chunk, which is what is the scale-up factor. And you use that because obviously you're going less into individual calculations for all the different embodied carbon life cycle stages. So you have to apply a scale factor that basically covers those chunks. If you look at it in the mid-level calculation, you'll see kind of a few more shades of blue, a few more shades of red. So those are all the additional life cycle stages that are being accounted for separately. It gives you a more robust calculation. And when you look at them compared to each other, the mid-level calculation will always be lower, just because there's less of those default kind of scale-up factors being added. And in reality, if there was an EPD done for the exact same product, you'd expect to see that even a tiny bit lower than that. So the methodology is intended to be conservative for that purpose. Good news, if you do find the methodology itself quite overwhelming and long to do, is that there is an automated embodied carbon calculator on the CIBSE website, which can be used. Essentially, you put in the inputs from the manufacturer form, and it will do the calculation for you. So that is an option as well, especially if you're kind of like a manufacturer or someone that's generating a lot of TM65 data points. That's something a resource that's available that can be used. And so the next two sections, we just wanted to highlight a few key takeaways from the topic papers and research papers that have been done following the TM65 methodology, and show you kind of where you can take some useful data points, hopefully, to be used. So as I mentioned, this one focused on residential schemes. So we looked at 4 different sizes of residential schemes, so down to single terraced houses, as well as 15-unit developments, 100-unit, and then 2,000-unit developments. The reason we did that is because obviously the design and the size of systems scales up differently depending on how big or small the building developments are. And within that, so as well as the 4 different sizes, we also looked at a range of about 14 different system options. So the ones on the left are all individual system options, and they're things, a gas boiler standard system was used as kind of a baseline, and what we're obviously seeing a lot of existing homes at the moment. And then we looked at different configurations for ground source heat pumps, air source heat pumps, VRF, direct electric, hot water heat pumps, and so on, as well as some communal systems, so more for the, larger developments, ambient loop systems, combined heat pump, boiler, CHP systems. We looked at a district heating network as well. So we tried to cover kind of the range of systems that we're seeing more commonly within kind of the UK market at the moment. And the process we did to get to those results really involved a lot of collaboration with manufacturers. This was done, I want to say, 2022, around that time. And it was still new. It was the first topic paper we had done following the methodology. So there was a lot of work to kind of get the industry engaged and try and understand the value of what this can provide. And we did have close collaboration with a lot of manufacturers that gave us their data points. And we worked with them to calculate what the TM65 values are. And from that, obviously, we had to get data points for all the different parts of the system that I mentioned before. And then we created kind of generic data points from those. So if we got, 5 heat pump data points, we created generic values for those, and we started to extrapolate that into what the system results look like. So an example here is for an air source heat pump. And you can see kind of on the graph on the right that we got. So we got about 18 different data points for an air source heat pump for different types of, for different kilowatt bucket sizes. And from those, we were able to calculate what the kilogram CO2 is per kilowatt of those heat pumps. And then you'll see kind of the dotted line on the graphs generate what those generic values are. So if you needed a generic value for a heat pump, you could go to that graph and kind of take that value, obviously understanding that it's an average. There's some conservativeness involved in that, but if it's an early stage design, it can definitely be used that way. all of these graphs are kind of they're all in the document itself. So they can all be found at the back for all the different range of products that we ended up getting data points for. We also have this graph that shows what the average kilograms of CO2 per kilogram is. So that unit, the kilogram CO2 per kilogram, that functional unit is used. It can be used most commonly across all products because all products have a weight. So you can see across everything that we looked at, from the boilers all the way down to kind of valves, pumps, MVHR systems, and so on, we had an average of about 9 kilograms of CO2 per kilogram. We also have in the document kind of double pages, which show you for the different sizes of the unit developments, what are the highest value systems and what are the lowest value systems, what's the average, and how you can compare between them. So if we just look at the graph on the right, kind of the bottom right, that shows you the whole life cycle embodied carbon of those systems. And you can see kind of almost directly that the direct electric at 36 comes out as the lowest embodied carbon value. You're kind of putting in less system components to begin with, which is why it results in that way. It doesn't have refrigerant, which can add on to it, and so on. And then you can also see which ones are the higher value systems. So this is really helpful, I guess, in early stages if you're trying to decide between system types. What are the factors that are going to affect the embodied carbon of the systems? And one thing to keep in mind that's covered in the document is that obviously this is just a focus on embodied carbon. We always try and emphasize and reiterate that decision making should be made on a whole life carbon basis. So although some systems might seem really low in an embodied carbon perspective, we really need to look at what the operational carbon is and how that building will run most efficiently as well, and kind of combine those together. It's no use of kind of one is really, really high and one is really, really low. Kind of having a balance and reducing as much as possible across both is really key. And then a couple more slides just to touch on the newest publication that was released on logistics centers, and that's TM65.3. So TM65.3 was a collaboration again with CIBC, but also with Amazon as well. And that was really helpful, obviously, with their kind of experience and involvement in the industry and logistics centers and distribution centers and so on. There was also some manufacturers involved, again, obviously, to give data points on material handling equipment and bespoke types of machinery that's used in logistics centers. So again, similar to kind of the concept of TM65.1, we started on a product level basis. Obviously, the products for this case study look slightly different and involves a lot more kind of conveyors, motors, cabling, and so on. And this graph just shows the range of what the embodied carbon kilograms of CO2 per kilogram were for this range of products. So obviously heavier machinery with a lot more kind of metal components and so on come out higher. And you can see it all the way down to kind of plywood support, which is used within some systems to support and kind of hold different types of machinery. And you can see the comparison between those. And then again, that product level, those product level values combined with the product quantities were built out to and extrapolated to calculate what the life cycle embodied carbon is of different types of, I guess you could say, systems or processes that are used in logistics centers. So here's a breakdown. And again, this might not be the usual thing that we see in building services or kind of just design units and residential schemes that we do more regularly. But if this is a space and kind of where we're seeing a lot of growth happening in distribution centers and data centers and so on, it's just to show that the TM65 methodology can be used to calculate other types of equipment as well. And this graph just shows the overall conclusion of kind of how those results were compared. We're comparing MEP products, which is kind of what's below the line, and material handling equipment, MHE equipment as well, and how they compare to each other. Again, just showing kind of that the methodology itself can be used for other types of equipment. It's essentially getting a split of what materials are being used in that product or piece of equipment and multiplying it by an embodied carbon value. I think that is that is our final slide going through the TM65 methodology and some of our case studies. I'm hoping that I think we're going to move to questions and hopefully we can answer any questions that have come up or you have.
Yeah, absolutely. Thank you so much, Yara and Miguel. This has been incredibly valuable, I'm sure, for our audience. And I can see some questions already sort of coming through. So we will move in on to sort of audience questions now. But if you haven't already, please do leave your questions in the Q&A section on Zoom. Just to sort of kick things off. So following the publication of the methodology and documents, so what's next then for TM65?
So that's a great question. So TM65, I guess, as we mentioned, has kind of been around since around 2021. And I guess the next thing coming most immediately is the topic paper on offices, which is something that's kind of in its final stages of being reviewed before being published. And hopefully that will again be a resource that can be used for the industry to take more benchmarks on office schemes. As well as that, something that has come up quite recently with other collaborators in industry and with CIBSE is how do we create a database or how do we have some sort of values that can be used and shared widely to push the industry further. So that's a conversation we're having close with CIBSE, and obviously the CIBSE Embodied Carbon Steering Group is heavily involved in that. To understand what a public TM65 database looks like, how do we create those generic values, and how that essentially becomes launched to be public forum. So it's something in the works and hopefully will be a useful resource for the industry.
Miguel, anything to add?
Oh, no. I feel like my wish list for like next topic would also be data centers. There's so much discussion around their environmental impact, and it would be great if CIBSE decides to like take the step in that direction. Because I feel like as an industry, we'll kind of like want to know more what is happening there, especially with AI and everything.
Oh. So we do have lots of questions coming through for you, of course. So we'll just start with the one from Jacob here. Is there any recent research linking facade performance and passive ventilation solutions to simpler MEP solutions with lower cost / carbon outcomes?
I can take this one. I can't recall any recent research at the moment, but the concept is there. If we can rely more on passive solutions, kind of like the passive house methodology, and using natural passive solutions like a good thermal performance, natural ventilation, we rely less on mechanical equipment, which down the line means less equipment, less materials. I can point to specific research that validates this, but it's kind of like the cornerstone of, for example, passive house, of making a building so efficient that you need the least amount of MEP equipment to make it useful.
Okay, anything to add, Yara, or should we move on?
No, I think that covers it.
Cool. So a question from Nick. So will consultants accept EPD documents that are not verified by third parties? Is that something you could answer for them?
I guess whether a consultant uses it is one thing, but to align with kind of the EN standard and the RICS methodology, so EPDs kind of need to go through their specific verification process in order to be accepted. And correct me if I'm wrong, Miguel, but I believe kind of depending on the system that you use, but if it was to be uploaded kind of onto OneClick or specific systems like that, it would need to be kind of verified and gone through that full EPD process before it could be accepted for those kind of open data sources.
Yeah, it's more than maybe specific requirements. For example, Mata 1 for BREEAM requires a certain level of EPDs to be used. That is mainly the limit. But if it's, for example, for a client or a consultant that they want a value, TM65 is still a very good approach to get a close value to what is expected. Maybe it's not something that you can submit, and you have to check really if you're submitting the results, what are the requirements for the components that you're using. But otherwise, consultants can accept it because it will be more accurate than if you can have, for example, an initial seed pump with a specific capacity, a specific weight. It's much more closer than if you just use an approximation of the closest DPD, maybe from a different country entirely, just because you couldn't find anything else. So it does bring an approximation, but if anything, some schemes require something else.
Great. Hopefully that answered your question, Nick. So on to another one from Sib Hussein. So do you see a difference between theoretical lifetime of a material and practical lifetime of a material? First question. Every situation is different and can influence wear and tear differently. So is the theoretical lifetime the minimum? And are you able to adjust the impact of the building in a later stage if materials last longer?
So I guess if we just start by pointing back to the TM65 methodology, so a lot of the lifespans for materials taken from that are from CIPSE Guide M, and they're kind of standard lifetime lifespans that are intended to be kind of it's intended for everyone to use the same ones, again, for to create kind of autonomy and consistent benchmarks across the TM65 data set. But I think the point is entirely valid, and that's where I think we're kind of shifting as an industry to a more circular economy approach. Materials should be made to be more durable and last longer, as well as even when they can no longer be used, not just kind of disposed of. So I think the reality is that there are materials that could last slightly longer, and it all depends on the wear and tear and how they're used. If you're doing a whole building life cycle assessment, the longevity of products could be adjusted based on how they are intended to be used. I would just say, referring back to the TM65 methodology, the methodology points to consistency, which is why those standard years should be used. But that's where the reporting forms the standard reporting forms can be helpful. That it's meant to really disclose your inputs and where you stray away from that. So obviously there are, like if you're doing a TM65 data point for a system and you found that there's a specific material that's quite unique to this product that hasn't been listed in the TM65 methodology because it's not a common one, you should still be accounting for it and you should still disclose where you're getting that from. So again, that's the same thing, I guess, for lifespans. If there's any specific kind of strong reason to stray away from those standard lifespans, it should just be disclosed. And I guess down to the individual to understand if there's kind of strong linked evidence as to why those materials would last longer in that specific case or not.
On that regard, applied to beyond TM65, there's a reason that we normally disclose or talk about upfront carbon and life cycle carbon. When we talk about upfront carbon, they're the emissions happening right now. We can measure them. They are here. It's like the manufacturer like doing something right now. When we speak about stages B and C, we're trying to predict future behavior. And any prediction has an uncertainty to it. We cannot know if a tornado is going to come around and just rip everything apart 2 years after everything is installed. So there's always this uncertainty, and the methodology to measure or predict future is slightly changing. It has changed between RICS 1 and RICS 2. So there's always this uncertainty with trying to predict that. RICS 2 as well has set some standard service life for different components. And we kind of like have to use them as a standardized benchmark. But again, there can always be a difference between what's actually happening versus what is predicted to happen, just because, well, we cannot know the future for certain.
Yeah, great. Thank you, Yara, and then thank you, Miguel. That's some great advice. How do you look at the use of thermal mass in balancing the thermal comfort of a building and the reduction in heating and cooling? The next question.
That's definitely, I think, that falls more into kind of the operational side, the operational carbon of how we go about assessments. And I think it links back to kind of what Miguel was saying on the importance of kind of passive house and designing fabric measures to begin with and how that can have a knock-on effect. So although maybe kind of improving the thermal mass of the building or increasing the thermal mass of the building can have an increase in some elements of embodied carbon of architectural elements or insulation or so on, it can then have a knock-on effect of not just the embodied carbon upfront, but again, the embodied carbon whole life. So there's a reduction in that aspect. I think the links between improving thermal mass and reducing overheating, I think, are studies that kind of are done alongside, whether it's TM59 kind of overheating methodologies or so on. I think the link there is quite strong. But yeah, where I can add on the embodied carbon side, I would say definitely that would have an impact because you're improving passive measures. Miguel, I'm not sure if there's any more from you to add there.
It's a good question because it really shows how all these different things relate to each other. Adding, for example, a concrete wall to help with thermal mass might be very good for thermal mass and comfort, but then you might be adding a lot of carbon as well. So it's always trying to strike that balance and see in case by case what you're gaining versus what you're losing. And there's no general rule because as well, if any case actually has some advantages, you can look at it like that, but there's no blanket statement that could help.
Oh, okay. So another attendee has said, great presentation. So thank you very much for that. Do you have any examples where embodied carbon data has been used to change the specified M&E systems?
I guess on case studies, maybe that we know of internally, kind of within Introba or design projects that we've been able to inform kind of at early design stages. We've definitely been able to kind of give clients the information or the understanding of why choosing one specific system might be better than choosing another from an embodied carbon perspective. Obviously, we have to loop that in and work really closely with so we're more focused on the sustainability team, but work closely with our mechanical and electrical engineers to understand what are the impacts of, if we did switch the system from an efficiency perspective, what could be the impact on that? And then again, referring back to the whole life carbon scenario and considering both alongside. So we've definitely had a few kind of, I guess, successful case studies of where we've been able to really inform clients in early design stages. And I do, just from some conversations with manufacturers as well, I've had some insights from them that even working with other consultants, they have been asked by consultants to either inform them of if they have EPDs or if not EPDs, TM65 data points, so they can also start to make those informed decisions. So I think it can definitely have, I think we're definitely seeing the link and the kind of knock-on effect between people asking for the embodied carbon of those products and how that can then influence what design choices are made and specified beyond that. Yeah.
To that, I would also add refrigerants. It's a conversation that wasn't really happening before, and sometimes it's very eye-opening for some mechanical engineers when we just put that graph and shows like the massive disparity between refrigerant types. And just having that conversation and be like, can it be propane? And just asking those questions, maybe the mechanical systems or the system that was being considered, they weren't even considering the type of refrigerants because it was not something that they had any preference on necessarily. But those conversations, like, okay, no, it's much better if we can go down this route. Can you make it work? Is this something that we can embed into the system? So I feel like refrigerants is the low-hanging fruit, but is one of the most impactful.
Great, thank you. The next question is on building heights. So in relation to the design principles presented for embodied carbon, there was little on building heights. Is there a sweet spot for mid-rise / high density housing in relation to embodied carbon?
Not that I'm aware of. I feel like there's a lot of factors that go into it. I mean, currently there's skyscrapers made of timber. We have like over 30 floors high buildings, all of timber. So I believe it's more on the material themselves and how it's being used. And also even when we get into that scale, the surrounding area, is it a car dependent city? Is it walkable around? When you factor in things like transport and things like that around the building, having a lot of low-rise buildings but are super spread out, that adds carbon in a different way in cars and how people move around. If you have a very dense high building, but it's all very dense and connected, you have people walking. So it's really hard when you talk a little bit about that because there's so many variables going on. I wish there was just a simple answer to that.
Maybe just a plug if this person is interested in reading a bit more research. There was a study that was done by some of our colleagues on specifically tall buildings and the impact of those from an embodied carbon perspective and draw some interesting conclusions. So Maybe something we can share with Grace after, or I'm sure if it was kind of controlled by tall buildings, something along those lines with search. It's quite a recent publication and could maybe help to answer some of those questions as well.
Great. Yeah, Yara, that would be really useful. If you can kind of send me over the link to that, we can then send that to sort of everyone that's joined the webinar today. So hopefully that will be really helpful. Next question is, do we limit the TM65 calculations to the building services, or we deep dive to the bespoke process-driven equipments within a building, which are non-standard?
So I guess I'm not sure specifically which products maybe that they would be referring to, but kind of touching on how we've been using it in the past. So for standard MEP products that we see, but also showing that last case study of TM65.3, which it wasn't intentionally written originally to be used for kind of, I don't know, conveyors or motors or specific types of like equipment that's used in logistics centers. But we found that actually the concept is the same. Or even going back to the methodology of how to calculate an LCA or an embodied carbon value that Miguel started on right at the beginning. It's a quantity multiplied by materials. So I would say it can be used for other types of services equipment that's being used in a building. I'd just be conscious, and I think it's really important for people to maybe we've gone through a few trainings kind of with CIBSE to train people on how to use the TM65 methodology. And we always get people to try to do it manually initially because you understand how different factors are affecting the final number. So I would just say if anyone is interested in trying to apply it to a non-standard product, maybe go through it through the manual route instead of using the automated calculator initially, just to be conscious of which life cycle stages are being affected. And maybe you'll find some parts of that are not directly translated. So a few things might need to be tweaked and then disclosed. So that's all I'd say, but it could be used essentially from how we've applied it recently.
Thanks, Yara. Apologies as well. I've got some building work actually happening outside my house, so I'm sorry if you can hear that on the webinar. The next attendee has said, apologies if I misheard this, but if Module D is not included in the life cycle embodied carbon calculations, does this mean recyclable products are penalised to some extent?
Well, maybe I didn't express myself well. Essentially, the idea here is that, as I said earlier, we cannot predict the future with certainty. The potential for something being recycled or reused is that it's a potential. There's nothing that mandates or that assures that that material will end up being recycled, reused, or repurposed or anything. So the way that it works is that for any life cycle calculations, you do not include that because it is not certain that it will happen, but you disclose it separately. So it is not that it's penalized. It is still being disclosed, and it can still be added like, oh, module D is X, and you can still compare between that and consider that as a positive thing. But because there is no guarantee that this is actually going to happen 50 years from now, they're actually going to recycle something, we cannot add it to the calculations because it's not assured, basically.
And I'll just add, so that's referring to the end of life and what happens with it at the end. But if it does have recycled products in it or recycled materials included in it, then of course that would still be accounted for in the TM65 calculation in the A stages when you're specifying what materials are being used. So it would definitely show a benefit if specific products included recycled components to begin with.
Yeah.
Okay, and we have a last question here from Luke Laverty at MBBJ. In the MEP suggestions for how to generally improve, are there material choices we can push for some as fabric, ductwork, or a specific material for trunking, racking, etc.?
I don't know for specific components, I guess, that I could point towards. All I would say is that just looking at embodied, so in the TM65 methodology or just generally on open source databases, you can see the embodied carbon coefficients of different types of metals. So just having an understanding of where the range is to begin with is probably a useful place to start. Again, we touched on things like aluminium being quite high compared to, I think off the top of my head, aluminium is about 13 kilograms of CO2, whereas steel is 3 kilograms of CO2 per kilogram. So you can already see kind of a difference between that. And I guess the last thing, touching on what we were just speaking about, recycled components. If there are specific, if you can use recycled metals or components, if we're, I think you mentioned tracking, or if we're talking about, I guess, pieces of equipment that don't necessarily relate to, I don't know, an efficiency, like something that's just to do with casing, things that don't necessarily get worn over time. And that's what we find with some specific MEP products, where maybe they have to replace specific fans or internal components, but actually the casing can last the whole building lifetime. It doesn't need to be replaced as often. So I think those are a few things I'd consider. So obviously the material choice, recycled components within those materials, and finally just looking at how those different components relate, and if there are specific ones that can remain as they are and you can only replace specific components between it. I would explore that, and that's probably a conversation that we had obviously with the manufacturers and so on. But those can have an impact. I'm not sure, did I miss anything, Miguel, that you want to
add? I mean, yeah, basically I would definitely highlight recyclable content and things like PVC, any metal that is essentially like what really drops the emissions. Also, you can start looking at more innovative materials like cardboard for ducts. Again, this is like a case by case thing. It might not work everywhere, but sometimes it's worth exploring to see if it is an option, if it can be used. There's also considerations when the service life. Do you have to replace it more often? So definitely it's not a silver bullet, but it is an option. So it's just good to see what's out there, because there's so much innovation going on in the sector that you can always find something interesting.
Thank you so much. We are almost at time, and I think that's the end of our sort of questions from the audience. Yara, Miguel, is there anything you just wanted to add before we finish up?
I would just say if it's for some attendees today, if it's your first time kind of hearing about TM65 and it's something you can get your hands on, definitely give it a go. I think it can, as we mentioned, it can seem kind of more overwhelming or maybe more complicated than it is, but it's really broken down to those two simple factors of how to do an LCA. So definitely give it a go. And if it's something that you want to do on a larger scale, then you can use the automated processes. And as well as trying the methodology, I would say if you are kind of involved in a design team where you can inform design decisions, definitely look at some of the benchmarks and some of those generic values that have been created. The research papers and the topic papers have been created for that purpose, to start to kind of give numbers to specific systems that we see in building types. So you potentially don't even have to do it from scratch. You can start to reference some of those figures, obviously until you get to technical design, and then you might need to make it more bespoke. But yeah, that's what the resources are created for. So hoping that they can be useful for other professionals.
Yeah, I cannot highlight that enough. I highly recommend taking a look at the TM65.1, 2, 3, 4 when it comes out, because in those, basically, we have collected entire systems for you and just applied the different carbon factors, and everything is ready and packaged in a very easy way, so that you can, if you're doing a residential building, you can look for your residential building, the different, if it's the size of it and the different system, and you get a number per square meter. They can just grab it and use it in your project. So I really highlight how useful it is for people that don't know how to even start accounting for MEP. This is a great resource that you can just go take a look at it, and you'll have the number for you. Just use it.
That's incredibly helpful, and also, yeah, thank you so much for your presentation today. I'm sure it's been incredibly valuable for our audience today. And yeah, to our audience, thank you so much for joining us today, and also for sending in all your questions. Yeah, thank you again. Huge thank you to Yara and Miguel for being here this morning. Oh yes, Harry is also sending his thanks from the audience. So thank you for presenting this TM65 methodology. And yeah, we'll now actually take a short poll for the audience to give us some feedback on the session. So this is always really useful for us in planning kind of future events like this. So yeah, I think we'll leave it there, and I hope everyone has a great weekend. Thanks.
Yeah,
Thank
thank
you
you.
so much.
Bye.